So now you should have completed in-class exercise number 3. I'll post the solutions for that. Most of the questions on there are pretty straightforward, so the only one I'm going to take a great deal of time to go through is this one, question number 3. And so in question number 3, I've given you the data for potassium's naturally occurring isotopes. And then I've asked you to calculate the relative atomic mass. And by relative atomic mass, we're just talking about the number that we see on the periodic table. So how do we do that? We do the following. We take the percentage of the first isotope, which is 93.26%, so 0.9326, times the mass of that element, of that isotope, 38.964 AMUs. We take the mass of the second element, times the mass of the second isotope, and then the same thing for the third one. We add those all together, and we get our mass of 39.099 AMUs that we find on the periodic table. Alright, so from here we're going to dig a lot more into the periodic table itself. So let's bring that back up. So again, as I said, we have there's 118 elements that we find on the periodic table. And we can see here how they're divided up. And actually, I'm going to jump down to a new slide and just give us a clean copy to work with. So our periodic table is divided up into what we call groups and periods. So the groups are the columns. So our first column in this periodic table we would call group 1, our second column group 2, and so on. As we continue to the right, we get all the way over to the last column, which would be our group 18. Now you'll also notice there's some other symbols up at the top. Some of them are labeled 1A, 2A, 3A, or 3B, 4B, etc. That's sort of an old terminology, and at this point we keep both of them on the periodic table because both of them get used fairly extensively. In this class I will in general try to just stick with the numbers, so groups 1 through 18, but you may come across different places where they use 1A and those labels as well. When we go across the table, or across a row, we refer to that as a period. So currently we have 7 periods in the periodic table. But as I said earlier, when that element 119 is discovered, or we should more accurately say synthesized, then we'll have to start an 8th row or an 8th period. Now, when I started talking about element 119, I said synthesized. And that's because once we get above uranium, which is naturally occurring, the remaining elements on the periodic table are not naturally occurring and actually have to be synthesized in a lab. And most of them are extremely short-lived. So at this point, some of these higher elements, Copernicum, Nihonium, Moscovium, etc., there's really not much practical purpose to them. But some of them do have uses. Some of these higher number elements, again, even though they have to be synthesized. So for example, element 95 here, americium, is actually a fairly commonly used substance. As you can see here, we find americium, very, very small quantities. Again, note that column on the left says 0.29 micrograms. But your typical smoke detector that you find anywhere has, almost 0.3 of a microgram of americium dioxide used as a detector. But again, this was an element that had to be synthesized. And you do that by basically bombarding two elements at each other at very, very high speed, high energy, and in an attempt to fuse them together. And that's something people have been doing for quite a while now. And that's what's led to filling out that entire row of the periodic table. And one of the people who's most responsible for doing that is this guy, Glenn Seaborg. And in honor of all his work, you can actually see there's an element on the periodic table, number 106, named after him. And that element was actually named after him before he died, making him one of the few people to ever have an element named after them while they were still alive, which led to him getting to take this rather unique picture, where you can see he's actually standing next to a periodic table while pointing at the element that was named after him. All right, so what is the importance in terms of how the periodic table is organized? So the most important thing are to look at the groups or the columns on the periodic table. And that's because when you're looking within a group, a column, the elements within a column on the periodic table have very, very similar reactivity. Now, we call this first group, some of these groups have very specific names. And again, I'm going to go to a new copy of our periodic table so we can draw some of these in. So our first column, or group 1, are known as the alkali metals. Now, if you've never seen anything or worked with the alkali metals, the most famous property of the alkali metals is that they're very, very reactive with water. And so because they're in the same column, they have very similar reactivity. Now, the reason they have similar reactivity is something that we'll get to much later in this course, but it actually has to do with their number of electrons and the way that those electrons are arranged. Elements within the same column on the periodic table have similar arrangements of electrons, and that gives them similar reactivity. Because as we'll learn later on, it's the electrons that determine how bonds form and what bonds form. All the way over here in group 18, we have what are known as the noble gases. Now, one thing you may have heard about the noble gases is that they don't react ever. Turns out that's not completely true. It's safe to say that noble gases don't like to react, but noble gases actually can and do form compounds. And we can see an example of that here. So the following image comes from Sigma Aldrich. Sigma Aldrich is a chemical supply company. And so if you look at your periodic table, one of the noble gases, number 54, is xenon. And here you can see not only does xenon bond to form a compound, but xenon difluoride is actually stable enough that it's commercially available and you can buy it. It's expensive. Yes, it's actually $179 for 1 gram of it, but it does exist as a compound. So one of the things I remember when I first took a chemistry class back in high school was I was told that yes, xenon can react, radon, krypton can react, but the higher elements on the table, helium and neon, they never form compounds. And probably when I was taking chemistry in high school, that was probably true. But we've recently learned and this is not loading very well. So let's do it. Let's bring this in a different way. So this is a paper that came out just a couple of years ago, 2017 to be exact. And you can see a stable compound of helium and sodium at high pressure. And what you can see is in the very first sentence they say helium is generally understood to be chemically inert. In other words, it doesn't react. However, they were able to find a stable compound. So they got 2 sodium atoms to bond to a helium atom. And it's stable at 113 gigapascals. Just to give you an idea of what that means, standard atmospheric pressure is just over 100 kilopascals. So we're talking about on the order of 1,000,000 times more pressure. But it was still able to prove that it can form. And so every element on the periodic table that's able to exist, in other words, some of these elements down here, the isotopes are too unstable. They don't live long enough to actually form compounds. But in theory, any element on the periodic table can form compounds. But what I want to show you now is that we do get very similar properties within a column on a periodic table. So if you're familiar with the alkali metals in group 1, you may know that they're very, very reactive with water. But as we'll see in a moment, as we go down the periodic table, that reactivity increases. So we're going to watch what happens when a series of different alkali metals is added to water. And again, what you're going to see is that the same thing happens with each one, but the reaction is a little bit more, changes a little bit as we move down the table.
But of course, it's not just the air that they could react with. There are other things as well. They could also react with the water. And this is what we're going to show now. The way you may have seen this in previous demonstrations, they normally throw the metal into some water. But there's all sorts of problems with this because the metal may have grease on it. It may be contained in a glass ampule if it's a really reactive metal like cesium or rubidium. So we're going to do this rather differently. We're going to add the water to the metal. Okay? We're going to use the same quantity of metal every time. And not the same mass, but the same number of atoms. So Mark has very carefully counted out the number of atoms, and he's got the same amount each time. So we're going to start off with lithium, and I'm going to add the same quantity of water every time as well. We're going to add 10 mils of water to our metal. So I'm going to take the top off. At the moment they're under argon, so there's no reaction of the metal with the air. Argon is heavier than air, and it's just sitting in the tube protecting the metal from the air, and we're just going to add some water. So this is lithium. You can see that it's bubbling rather nicely. It's forming hydrogen gas. And in fact, we can see the chemical equation for the reaction. It's the same chemical equation for all of the elements. We have the metal reacting with water to form the metal hydroxide and releasing hydrogen gas. So every time it's the same equation. But what we're trying to do now is see if we can tell the difference between the reactivities of the different metals. So out with the lithium, in with the sodium. Now again, it's the same quantity of metal, but does it react any more vigorously? I'm going to add the same quantity of water. All right, so the sodium, certainly a lot more violent than the lithium. In fact, it caught fire. Notice the yellow colour. This is the colour characteristic of excited sodium atoms. So the sodium was clearly having a good time there. Right, potassium. Again, the same quantity, the same number of atoms. We're trying to keep everything as controlled as possible. The same quantity of water. Just as an added safety precaution, I think I'll put this on. Right, so potassium now, and water. Getting more vigorous. Okay, maybe we can, yes, that's a good idea. We'll just remove some of the smoke so you can see the next one more clearly. Now some rubidium. We'll have an extra blanket, I think. Here's the rubidium in the tube here. We can see the rubidium metal under a blanket of argon. And again, it's exactly the same quantity. Every time we're using the same quantity. This is now rubidium, same quantity of water. Beautiful blue colour. That's the colour of the rubidium flame, remember. We need to wait for that to go. Okay, we'll just wait for this to clear because this is a one-off experiment here. The amount of cesium that we're using is 5 grams, and it costs several £100. So here is our cesium. And again, if we just show this on the camera there. So there's quite a bit of the metal down in the bottom of the tube, and again, it's under a blanket of argon. Okay, so it will not react with argon gas. When I take the stopper off, it will not be reacting with the air because the argon is heavier than air. And so that will protect it until it comes into contact with the water. And we've used the same quantity of every metal here, the same number of atoms. Okay. Here is our water. And there we go. Not bad. Oh, I'm pleased that one's over. Good. Right. So actually cesium though, I mean it is the most reactive. There's no doubt it's the most reactive of all of the metals and reacts very, very quickly. It's also heavier than water, Both rubidium and cesium sink to the bottom of water, so that's one of the reasons it reacts very quickly. But I always think that the best reaction, actually, is with sodium and water. This is my favourite, because I think the sodium has more of a chance to sort of build up the tension and heat up. It's much more interesting. So we're going to try some more sodium now on a slightly larger scale in the tank here. Okay. Notice the amount of francium left. It's still decreasing. There's not a lot left now. So that's why we're not going to be looking at any francium. Okay, here is our sodium. Going to drop this into the tank and run away. Okay. Can't see where it is. Oh! And there we go. Nearly coming to an end.
So as we can see that we get very similar reactivity within the elements within a group. We get different levels of reactivity, but the overall reaction is very, very much the same. So in an effort to not make these files too large, I'm going to stop this video here, and we'll pick up with the next video right away.